Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. In this video, I'm going to be covering two ways that you can transfer energy, heat, and work, and going through some example problems. Let's get started. In previous videos, we discussed that the two main ways that energy is transferred is through the process of work and through heat. And so we could say, if we wanted to calculate the overall internal energy of an object, we would have to be aware of how much heat is either being gained or lost by the system, and how much work is either being done or done for the system. And we add those two up to figure out the overall energy change that is related to that process. Now, it's important to note that while energy, as we mentioned before, is a state function, that heat and work are not state functions. And so those can have some fluctuation to them, but again, that end result will be the same. So you'll want to remember this chart, and we're going to use this to help us to figure out what sign do we apply for to certain values as we are reading a problem. So if the system is gaining the heat or it's absorbing the heat, we're going to assign that heat value as a positive number. If the system is releasing the heat, letting it go, then it gets a negative value. If the work is being done by the system, again, think about yourself, you might be exhausted, and so then you would give a negative value to it. And if someone else is doing the work for the system, the surroundings does the work, it would get the positive value. So again, this terminology is in reference to the system, what's happening to the system. And so you may have to use context clues about the surroundings to help figure that out. So again, two ways that we're going to be exchanging is through the heat and the work. As we move through this chapter, we are going to have specific equations that we're going to utilize to calculate the heat or the work of an object. But right now, we're just learning about the basic transfer and calculating that internal energy. So again, main ways that we're exchanging energy between the system and the surroundings is heat and work. So this is just a good graphic representation for you to understand what's happening, how heat is playing into things, how work is playing into things, and what impact it has on the overall internal energy. All right, so let's look at this example. It says a white ball, or the cue ball, has an initial amount of 5.0 joules of kinetic energy. So it has some amount of energy stated before it. Now, as I hit the cue ball in motion, it's going to start to roll. And so as it starts to roll, there's going to be heat that's generated because of the friction between the ball and the table. And so there's going to be some amount of heat that's lost. Well, since the cue ball, the thing we're studying, is losing it, we would assign that heat value as a negative value. We're losing that heat to the surrounding area. And then after a little bit, it bumps into the purple ball, and it's now able to transfer the rest of its energy into the purple ball and put it into motion. And so again, in this case, the object that's doing the work is the cue ball. It had to bump into the purple ball to put it in motion. So because the system did the work, we would assign it as a negative value for that work that's being lost. Okay, so work and heat. And so when we go to calculate the change in internal energy, we're going to look at the overall heat and work that was being created or used, and make sure we assign the proper signage to it. In this case, both would be negative because they were both done or produced by the cue ball, the system that we're studying. So because the cue ball created the friction and the heat, it's a negative value. Because the cue ball did the work to get the purple ball in motion, it's also a negative value. When we add those two together, E equals Q plus W, the heat, which is Q, W, which is work, we get an overall change as negative 5.0. which we see is equal but opposite to what it started. Remember, first law of thermodynamics, energy cannot be created nor destroyed. Okay. Now, on this particular example, we're seeing that the amount of heat that's lost in a smoother table is about 0.5 joules. And so again, overall, when we calculate the amount of heat that's lost along with the amount of work that was done, we're at negative 5.0 joules that was generated here, or transferred. But now if we had a slightly rougher table, so if we had a rougher table, that means there's going to be more friction. As there's more friction, that means that more heat will be generated and lost by the white ball, the cue ball. And so in this case, it's losing 3.0 joules. And so it's in the negative 3.0 for the heat. And then it's going to bump into the purple ball. And the purple ball now still will get that energy transferred, that kinetic energy, but there will be less that's available. So how much is available? Only 2 kilojoules, or excuse me, 2 joules. And so again, because the cue ball, the system, the thing that we are studying produced the heat, did the work, we assign both of those as negative values. And when we add the two together, we still get that negative 5.0. Again, the energy is a state function. So the overall answer that we're looking for should be the same regardless of the path that we took to get there. So if we put all that together in the previous example, the delta E, regardless of the situation, whether it be the smooth table or the rougher table, remained the same. But you notice that Q and W, the heat and work, were not. On the rougher table, far more heat was lost, which means less work could be done on the purple ball. And as a result, the ball likely did not travel as far. But the thing we want to remember in this case is that that energy is a state function. It's dependent on the amount of energy that's being, or heat that's being lost and or work that's being done based off of the surrounding environment. Okay. All right, so let's put all that together. And so in this question, it says if the burning of the fuel in a potato cannon performs 855 joules of work on the potato and produces 1422 joules of heat, what is the delta E, the energy for burning of the fuel? So in this case here, we have to think about, okay, well, what's the system? In this case, the thing we're studying is the burning of the fuel. That's our process. So the delta E is for the burning of the fuel. That is our system. And so we have to ask ourselves, well, who performed the work? Well, it says if the burning of the fuel caused that work to happen, that means that the work is being done by the system. And so we would give this a negative value. And then it also goes on to say, and burning the fuel produces the heat. So that means the system produced the heat. So that would also be a negative value. So when we're calculating the energy of our system, it's going to be the heat, or the Q, plus the work. But now we have to change the signs. So we would say the heat, which is negative 1422 joules, plus the work, which is negative 855 joules. And then we would add the two together. So when we do that, we end up with negative 2277 joules that ultimately was lost or released during this process. Okay, check your answers. Awesome. Okay, so we'll move on to the next one. It says reacting 50 milliliters of sorry, I can't see it. So the next problem says reacting 50 milliliters of H2 with 50 milliliters of C2H4 produces 50 milliliters of C2H6 at 1.5 atmospheres. If the reaction of the gases produces 3.1 times 10 to the second joules of heat, and the decrease in volume requires the surroundings to do 7.6 joules of work on the gases, what is the change in internal energy? Okay, so again, when we think about what our system is, what we're studying is this reaction, these gases. And it goes on to tell us that, well, if the reaction produces 3.1 joules times 10 to the second joules of heat, we know that since the reaction did it, the system did it, we would assign that as a negative value. And the decrease in the volume requires the surroundings to do. So that means somebody else did the work for us. So that means we would assign this as a positive value. We would then plug those into our equation for Q plus W. So our energy, our delta E, the internal energy, would be equal to negative 3.1 times 10 to the second joules plus positive 7.6 joules of work. So we'll add the two together. So negative 3.1 e to the second plus 7.6. And what we end up getting is negative 302.4, or with proper sig figs, negative 3.0 times 10 to the second joules would be equivalent to the eternal energy. So go ahead and check your answers. And hopefully that worked out for you. I hope this information helped you understand heat and work and how to assign the proper signage for them based on who is producing the heat or who is doing the work. Be sure to like, comment, and subscribe, and let me know what other content you would like to see. Make sure you guys come back to see more videos. We're going to be getting into more energy related topics in future ones. Have a great day. Talk to you later.